Experimental FEA adds finite elements to the same 3D structure model that is used for displaying experimental mode shapes in animation. In this chapter, a finite element model will be constructed by adding plate elements to a photo model of the gym beam. This model will then be solved for its analytical modes, and they will be compared with its experimental modes. To display the experimental mode shapes of the gym beam, execute help, demos, frequency-based ODS demo, to open the gym beam project file. Open the Mode Shapes Shape Table window from the project panel. Click on each of the shape buttons in the Shape Table window to display its mode shape. Building a finite element model and solving for its FEA modes prior to performing an experimental modal analysis, or EMA, has several advantages. 1. The number and density of modes in a certain frequency range is known. 2. The approximate modal frequencies are known. And 3. The dominant direction of motion of each mode shape is known. With the mode shapes of the gym beam in animation, execute animate, direction, X direction to turn off the X direction of animation. Execute animate, direction, Y direction to turn off the Y direction of animation. Click on Shape 1 in the Shape Table window to display the 165 Hz mode shape. Notice that this mode looks like a rigid body mode of the beam when only the Z direction is displayed. Of course, it would be very unusual for a mode at 165 Hz to have a mode shape like this. Nevertheless, if experimental data had only been acquired in the Z direction, this is the EMA mode shape that would be extracted from the data. Clearly, the dominant direction of motion of this mode must include either the X or Y direction. Had the X and Y directions not been measured in EMA, this lack of information in the mode shapes is called spatial aliasing. The FEA assistant in the Experimental FEA option will be used to build a finite element model of the gym beam. The gym beam test structure was constructed from three 3/8" nominally thick aluminum plates fastened together with cap screws. The overall dimensions of the gym beam are 12 inches long by 6 inches wide by 4.5 inches high. The aluminum plates will be modeled using FEA quad plate elements. To build an FEA model of the gym beam starting from the photo gym beam model, the following steps will be followed. 1. Make a 2D profile of the beam from the photo model. 2. Extrude the profile into a 3D plate model. 3. Add an FEA quad object to the plate model wherever there is a quad surface. And 4. Solve the FEA model for the FEA modes of the structure. To create a 2D profile, execute animate, draw to terminate the mode shape animation. Select points from the Edit Object list of the Structure window toolbar. Hold down the Control key to enable Draw, click Select, and select points on the photo model to define a 2D profile. Execute Edit, Copy Objects to File to copy the 11 selected points to a new file. Click on the New File button in the dialog box that opens and enter FEA Stick Model into the next dialog box that opens. A new structure window will open containing the 11 profile points. To complete the 2D profile, line objects will be added between the points and all lines and points will be grouped into a new substructure. Select Lines from the Edit Objects list on the New Structure window toolbar. Execute Edit, Add Object. All of the points on the model will be displayed. Starting at one end of the profile, click on a point and then on an adjacent point to add a line between them. Repeat these steps until 10 lines connect all of the points in the profile. Execute Draw, add selected objects to substructure, and click on the New Substructure button. Enter Profile into the dialog box that opens, and click on OK to create a new substructure containing the profile. Next, the 2D profile will be scaled to the proper size of the real gym beam and then extruded into a 3D model. The actual gym beam is 12 inches long by 6 inches wide by 4.5 inches high. Execute Draw, Drawing Assistant, to open the Drawing Assistant tabs in the FEA stick model window. On the Dimensions tab, uncheck Lock Aspect Ratio and enter the following dimensions: X, 12 inches, Y, 0 inches, Z, 4.5 inches. On the Position tab, press the Global button to center the substructure about the global origin. On the Extrude tab, enter Length 6 and Points 3 and click on the Extrude button. The points on the 3D model need to be numbered to coincide with the point numbers of the test points on the Jim Beam PhotoModel. This is necessary in order to calculate correct MAC values later on, using matched DOFs between the FEA and EMA mode shapes. Execute Draw, Number Points, to open the point numbering dialog box. Press the Clear All button in the Number Points box to clear all of the existing point labels. Click near each point to number it. When you are done, all 33 points should be numbered. An FEA model will be created by adding FEA quad objects to the 3D stick model created in the previous sections. The FEA assistant will be used to add an FEA quad object wherever there is a surface quad object on the substructure. The 3D stick model only has 20 surface quads on it, which is too coarse for obtaining accurate FEA mode shapes to compare with the EMA mode shapes. To increase the number of FEA quads, each surface quad will be meshed into 4 surface quads. Meshing the substructure will create 80 surface quads. Therefore, 80 FEA quads will be added to the model using the FEA assistant. Make sure that the profile substructure is selected. Execute Draw, Mesh. Enter 1 in the dialog box that opens and click on OK. The 3D stick model should now contain 105 points and 80 surface quads. Before adding FEA objects to the model, engineering units for the FEA plate element properties must be chosen in the structure window. Execute File, Options in the FEA stick model window. On the Units tab, choose Pound Mass for mass units, Pound Force for force units, and Inches for length units, and click on OK. To create the FEA model, 80 FEA quad objects with aluminum properties and a 3/8 inch thickness will be added to the stick model using the FEA assistant. Execute FEA, FEA assistant to open the FEA assistant tabs. Make sure that the profile substructure is selected. On the Add FEA Elements tab, press the New button on the same line as the Plates button. The FEA Properties dialog box will open. Select the Plates tab and press the New button. A new plate will be added to the Plate Properties spreadsheet. Click on the cell in the Material column and select Aluminum from the drop-down list. Enter 0.375 into the cell in the Thickness column. Click on the OK button to close the FEA Properties box. Press the Plates button on the Add FEA Elements tab to add 80 FEA quad plate elements to the substructure. When the Plates button is pressed, an FEA quad object will be added wherever there is a surface quad object on the selected substructure. Since there are 80 surface quads on the model, 80 FEA quad objects will be added to the model. The FEA model is now ready to be solved for its FEA mode shapes. To solve for the FEA modes of the Jim beam, execute Display, FEA Objects in the FEA Stick Model window to turn off the display of FEA objects. Execute FEA, Calculate, Normal Modes. A dialog box will open summarizing the elements that will be used to calculate the modes. Click on Yes. Another dialog box will open asking how many modes to calculate. Enter 20 and click on OK. The normal modes of the Jim beam will now be calculated. After the modes have been calculated, a dialog box will open allowing you to name the shape table file into which to store the FEA modes. Enter FEA modes into the dialog box that opens and click on OK to open a shape table window with the FEA modes in it. Notice that the FEA mode shapes have 630 degrees of freedom, 315 translational DOFs, and 315 rotational DOFs. Only the translational DOFs will be displayed in animation and compared with EMA mode shape components at matching DOFs. Notice also that the first 6 modes have very low frequencies. These are rigid body modes. There are 2 ways to compare 2 shapes: graphically with the animated comparison display, or numerically by calculating their MAC value. Both the graphical and MAC value comparison are done for a pair of shapes by executing the Animate Compare Shapes command. Before using this command, however, both the FEA and EMA mode shapes must animate correctly on their respective models. To animate the FEA mode shapes on the FEA Stick model, in the FEA Stick model window, choose FEA mode shapes in the Animation Source drop-down list on the toolbar. Execute Draw, Assign Measurement Numbers. A dialog box will open. Click on OK to create measured animation equations for animating the FEA mode shapes. A dialog box will open, listing the number of measurement numbers assigned to the DOFs of the structure model. Click on OK to close the dialog box. The FEA model is now ready to display the FEA mode shapes in animation. Execute Draw, Animate in the FEA Stick model window to initiate animation. Click on each shape button in the FEA Modes window to display its shape in animation. Execute Animate, Draw in the FEA Stick model window to terminate its animation. Make sure that the Structure Photo Jim Beam and Shape Mode Shapes window are open. Execute File, Options in the Photo Jim Beam window and check Show Comparison MAC on the Labels tab. Execute Draw, Animate in the Photo Jim Beam window to initiate animation. Execute Animate, Compare Shapes in the Photo Jim Beam window to initiate comparison animation. Select Structure FEA Stick Model in the dialog box that opens. Both models will animate together, with the EMA model on the left and the FEA model on the right. The EMA Mode Shapes table is displayed below the structure window on the left, and the FEA Modes table on the right. The best matches between the FEA and EMA mode shapes based on their MAC values are listed in the following table. Click on each mode shape pair to display their shapes and MAC value. Drag the horizontal scroll bar at the bottom of the structure window to overlay the two structure models during animation. If two mode shapes are animating out of phase with one another, execute Display, Complexity Plot in the Shape Mode Shapes window to open the Shape Complexity Plot. Execute Display, Shapes Normalized in the Complexity Plot window, and drag the plus-minus line to rotate it until the animating shapes are in phase with one another. It is clear that even though the FEA modal frequencies are all different than the EMA frequencies, the mode shapes of FEA modes 8 through 17 closely match the mode shapes of EMA modes 1 through 10. By animating and overlaying them in the previous section, 10 of the FEA mode shapes appear to match well with the 10 EMA mode shapes. The Modal Assurance Criterion, or MAC value, is a more precise numerical method for comparing two shapes. In order to calculate a MAC value between a pair of FEA and EMA mode shapes, both shapes must have shape components that correspond to the same DOFs on the structure. Recall that the 33 points in the FEA stick model were numbered to match the 33 points in the Photo Jim Beam model before the FEA stick model was meshed. Consequently, the FEA mode shapes have components for DOFs 1X, 1Y, and 1Z through 33X, 33Y, and 33Z that match the same physical points as the shape components of the EMA mode shapes. Hence, MAC values can be calculated between the two shape tables, Shape Mode Shapes and Shape FEA Modes. The MAC values between the pairs of FEA and EMA mode shapes were listed in the table in the previous section. Since no particular shape DOFs were selected, all of the matching DOFs from both shape tables were used in the calculations. In this section, we will compare MAC values when only the Z directions of the DOFs are selected. Make sure that both shape tables are open in the work area. To calculate MAC values for the Z direction only, execute Edit, select DOFs, By in the Shape Mode Shapes table. In the dialog box that opens, select Direction from the drop-down list and Z in the list below it. Press the Select button followed by the Close button. The Z direction DOFs should now be selected. To open the MAC window and display the MAC values, execute Display, MAC in Shape Mode Shapes window. A dialog box will open. Select Shape, FEA Modes, and click on OK. The MAC window will open. Hover the mouse pointer over each of the vertical bars to display its MAC value and shape pair. The MAC values between the best matching shape pairs are shown. Notice that all the MAC values are now above 0.90, indicating that 10 consecutive FEA shapes are essentially the same as 10 consecutive EMA shapes. This is a strong correlation between the analytical and experimental mode shapes of a real structure. The MAC values improved when only the shape components in the Z direction were used because most of the mode shapes had motion predominantly in the Z direction. Since the EMA modes have experimental error in the X and Y directions, By removing these directions from the MAC calculation, the MAC values improved.